Okay, good morning, everybody. We'll get started with today's session on the Roman Coronagraph and new missions. And it's my pleasure to introduce Bertrand Mennesson, who's going to talk about the Roman Coronagraph instrument and its applicability to HWO. Thank you, Bertrand.
Yeah, thank you very much. Thank you very much. Glad to see you all. When I started in the field of direct imaging 30 years ago, I didn't think that 30 years later would be that many working in the field of direct imaging of yet to discover exoplanets. So I'm really happy to be here with you today. I will talk to you about the Roman Coronagraph instrument and its applicability to HWO. So there are a number of talks this week about Roman. I'm not the only one. So there are the following talks about the commissioning, the designing of the observation phase of Roman, some reference star vetting by Justin Holm, and some high order wavefront sensing and control by Alexi, and a number of posters that I invite you to go have a look at if you're interested in Roman and what it can do for you. So the Roman Coronagraph in a nutshell is what I will start with. I will describe to you the observing modes that are guaranteed or just have been added. The INT lab results and expected in-flight performance of Roman, the potential science observations that we'd like to do with them, and you'll hear more about that in Skylar's talk. A little bit of a consideration of disks versus planets, and you'll see that Roman is really good for disks and not so good for exoplanets. And a few words about the community participation. Okay. So the Roman Coronagraph is a stepping stone toward the HWO. It's the visible light high contrast technology demonstration for HWO. It's one of the first base coronagraph with active wavefront control. I think it's the first one with 2 DMs, large format, 48 by 48 DMs. The requirements are not too ambitious. It's to reach nominally a flux ratio detection limit of 10⁻⁷ at 5 sigma at 6 lambda over D. But you'll see that we have designed the instrument to largely outperform this requirement, which is only a technical requirement for Roman that we need to pass. In fact, the predicted performance is at least 4 times better than this, based on the TVAC testing. So in reality, this is what it looks like. It's big like a piano. This is the Align optical bench on the left to scale, with the electronics palette on the right. So that gives you a sense of scale for the Roman Coronagraph instrument. So it captures a number of technologies that we like to demonstrate for the first time in space all together. Of course, ultra-precise wavefront sensing and control. You can see the focus control mechanism and the fast steering mirror on the left here. The pair of DMs that I mentioned before. A number of high-contrast coronagraph masks. This is a pupil mask, so one family, and an HLC mask in the focal plane, so the second family. We test both families with Roman. A pair of low-noise photon-counting EMCCDs, which are fairly identical, one for the science camera and one for the wavefront sensing camera, which is going faster. And finally, we're going to try post-processing, and we heard a lot about this yesterday. And I hope you'll be as inventive with Roman as you've been with JW. So, and of course, all these technologies have to work together. This is a sketch of the beam path for Roman, with some of the elements that I mentioned before, the FSM, the FCM, the DMs. And as I mentioned, we can actually rotate some of these masks to actually emulate 3 different types of modes. We call them wide field of view imaging, narrow field of view imaging, so WFOV and NFOV. And SPEC is the spectroscopy mode, which is a single point source spectroscopy mode with a slit. So fairly simple spectroscopy mode, but there is one on Roman that we can use. And the 2 wavefront sensing and science cameras that I mentioned before. So we can alternate between any of these modes when we observe. So in bold here, you've got the fully supported mode, which is HLC at 575 nanometers, and the other 3 so-called best effort modes, which we've actually tried in the lab. But we only need the first one to pass the technical requirement for Roman, and the other 3 are also offered to the observers, but are more shared risk. And we have plenty of other modes that I don't have to describe here, I don't have the time to describe here, which were contributed by EXEP, which have not been tested but are on the instrument as well. I invite you to look at Eric's paper from last year about this for discussion of all the modes, or we can talk about it. So this was 2024 when we went into TVAC. You can see the instrument here with the radiators, the control electronics, the optical bench going into the vacuum testing at JPL. The results that we got were quite extraordinary. They actually demonstrated that we met requirements for 2 coronagraphs. Remember, there's HLC-type coronagraphs and SPC-type coronagraphs. So we actually demonstrated that we met the requirements not with 1 but with 2. This is the HLC here on the left. And so we got a raw contrast of 3.3 × 10⁻⁸, average between 6 and 9 lambda over d, which corresponds to the 2 white lines here. It turns out it meets the requirements of 10⁻⁷ planet-to-star flux ratio detection limit. And in the wide field of view case, which is the case on the right, we also did meet the requirement with about the same level of contrast demonstrated. What's important to realize is that this performance demonstrated in vacuum with the in-flight instrument is not necessarily the limiting one. It was really set by the time that we had. We had already met the requirement. We pushed a little bit more, but we were limited in time. In TVAC, we still took 24 hours, 7 days a week, 3 shifts a day to accomplish this. So it's a really fantastic feast. So here's a movie of the starlight suppression, starting from a bad wavefront to all the way to a really deep dark hole, as demonstrated in TVAC with HLC. And mention Eric and others who have been kind of heroic in making this happen in 2024. And we hope to do that again on Sky at the end of this year. So you've seen this graph many times, so I won't describe the axis, but it's flux ratio to host star versus separation. And right now we're in this region of parameter space around here. It's a little bit better actually than this if we put the latest HWO results. But we're sensitive to planets down to 10⁻⁶, 10⁻⁴ to 10⁻⁶, depending on separation. And Roman is going to really get us to, we hope, to the regime of 10⁻⁸, 10⁻⁹ on our way to HWO, which is targeting this type of planets at 10⁻⁻10-ish contrast around 0.1 arcsecond. So it's a stepping stone, really. We don't think we could go from here to here in one step. So Roman is going to get us partially there. And I think that if we have to predict today where we're going to be in terms of contrast with Roman, this is going to be somewhere in this yellow region. So probably better than TVAC. Integrating for long times, we're going to get somewhere in that yellow region. That would be my prediction. Or we'll see in terms of planet-to-star flux ratio detectable. So how relevant is it really to HWO? And we predicted detection limits which are 100 to 1,000 times better than the state-of-the-art at visible wavelengths. That's true. We will test speckle calibration methods applicable to HWO in a relevant contrast regime where both amplitude and phase matter. That is true. But we are still 10 to 100 times factor away from HWO detection limits needs. So how is that really relevant to HWO? Well, the answer to that is that in spite of the contrast being more modest than we need for HWO, most functionalities and subsystems have actually predicted performance in family with HWO technical needs. And the reason for that is that the ultimate contrast performance is really limited by the heavily obscured entrance aperture of the telescope, rather than the telescope stability, which is exquisite even in Earth orbit, but even more in L2. So it's going to be an extremely stable telescope. But we would never pick an entrance aperture like this with heavy struts and a large secondary obscuration for HWO. And if you're interested in the details about this, you can read my paper from 2020. On the science side, we will barely skim the top of the exoplanet population on mature stars. So remember what was said yesterday. With JWST, you see a lot of planets. You're in the mid-infrared. They are much brighter. They are 10⁻⁴, 10⁻⁵, 10⁻⁶. But really in the visible, for mature planets, you really need to hit that 10⁻⁹-ish contrast or flux ratio. So that's really much harder. So we'll also have limited single object spectroscopic observations rather than multi-object, like we hope to get with an IFS on HWO. However, we think that it's going to be capable of detecting disk and low enough density levels to inform HWO target list, and I'll get back to that in a minute. So this is the delivery to Goddard 2 years ago now. So you can see that it takes really a village to build this. So that the first image here is the team at JPL before the Coronagraph was sent to Goddard and integrated to the rest of the observatory at Goddard in May of 2024 successfully. So the overall schedule is we know it pretty well. The instrument was delivered to Goddard in 2024. A bunch of tests have been going on since, all successful. NASA carried this no later than date for launch, which is May 2027. But in fact, we are working internally at the project level on a much earlier launch date, sometimes in September of this year. So that's going to go much faster, we think. We're going to start with the commissioning phase that Eric will describe in details to you right after my talk, which is the first 90 days after launch. And then we're going to start the so-called technology demonstration phase. We call it regular observation now, but it's the rule of the game hasn't changed, which is we're going to spend about 3 months of observations over the first 18 months of the mission to exercise the coronagraph. So if that technology demonstration phase is successful, there might be some potential follow-on observations. We certainly hope so, but it's not guaranteed right now. So the baseline, as I said, is about 90 days during the first 18 months. The top priority is really to achieve our requirements technically and show that this is officially a success. So for that, officially, for NASA, we only need to meet that so-called TTR5 requirement that I mentioned to you before, which is 10⁻⁷ at 6 lambda over D. Then, as time resources allow, we want to push the performance limits of the instrument in many different regions of parameter space. The baseline resources are not yet sufficient to support all best effort and unsupported mode tests. But however, the guiding principle for decision making and prioritizing these modes is, and has been for a long time, to maximize the long-term value to HWO and the science community, and to use scientifically interesting targets whenever possible. So I'll give a few examples of scientifically interesting targets, and I think Skylar will talk a bit more about that in a minute. But, no surprise, we're going to be looking at self-luminous planets, reflected light planets, and bright and faint debris disks. So I'll spend a few minutes on these. So for young self-luminous massive planets, we're going to be looking at objects like this at visible wavelengths for the first time. Generally, these objects are very hot, so they have an SED that looks like this. They are pretty faint at truly V-band. They're already brighter at 900 nanometers. So we are wondering what are the cloud properties of young massive planets? How inflated are they? Are they metal-rich? We're going to be looking, for instance, for sodium and potassium. And generally speaking, CGI will be able to fill out the SED of these objects in the visible for the first time with broadband photometry and spectroscopy. And I believe either beta peak B or HR 8799, one of the planets has been observed at 900 and some change nanometers, but really at visible wavelengths, there's no detection. And the first ones will come with CGI. So we hope to get the first reflected light images of a mature Jupiter analog. That's one of the big goals for CGI. Once again, trying to answer the question, are cold Jupiter analogs cloudy or clear? Measure their albedo at short wavelengths. What are the masses of known radial velocity giant planets? So for that, we're going to need to measure the orbit by constraining the inclination of the system with 2 or 3 imaging epochs, and you'll hear about that in the observation planning. And then if we have detected one, and after we have detected one, and know really where it is, when we're going to devote time to do a spectroscopy and trying to answer some of the basic questions like, are Jupiter analogs metal rich? Do they have a lot of methane? For instance, that we can look for around 730 nanometers. Can we constrain metallicity of these objects if cloudy? That's one of the goals. In terms of cold debris disk, we're going to be looking at the inner counterpart of this very extended debris disks that have been resolved with HST and even more with JW, but not the very inner region. So if you look at this particular object here, it really illustrates it well, that we're going to be looking at what is traditionally the region where we cannot see with HST or JWST. Here the outer working angle of HLC and SPC, and you can see that they cover that inner region with a dark hole and gives us access to much smaller scales than presently accessible. Another case, of course, is dyspolarimetry with a Coronagraph. So the poster child here is HR4796A, which has been observed in the near-infrared by Marshall Perrin. And you can see the images, both unpolarized and polarized. But there's been no detection of unpolarized light at visible wavelengths. What we have now is polarized spheres, impole images at visible wavelengths, but no unpolarized images. That should be a slam dunk for CGI if you can do polarimetry at all. And then another one, the last one that's really close to my heart, which is exozodi, which is going to be a big problem and a big challenge for HWO, because as you get in the habitable zone, you get all of that dust. You wonder if it scatters a lot at visible wavelengths. It's been known for a long time that exozodi is a problem, or might be a problem for detectability of exoplanets. We looked at it in the mid-infrared with KI and LBTI over the years, but we still don't know what exactly it is going to contribute at visible wavelengths in scattered light. There's a bit of extrapolation needed to know that. So we're going to make a direct measurement with CGI for the first time. There was a recent paper from Ewan Douglas in 2022 and collaborators that showed that with CGI we should be able to access the habitable zone of tens of targets for HWO in reasonable exposure times of maybe a month, etc. So we're going to start with a pilot program looking at probably 5 or 6 of the favorable targets, covering a wide range of Zodi levels, and demonstrate the feasibility, hopefully, of that technique to constrain many more exozodi levels around sun-like stars with CGI in preparation for HWO. Okay, so I talked a little bit about disks and planets, and I want to say a few more words here that are a bit technical, but basically the big difference between Raman and HWO is the core throughput. And I will say the eta P, which is represented here. So kind of understandably, we concentrated a lot on getting a deep raw contrast over the whole broadband with CGI. But in doing so, we got rid of a lot of the planet light as well. And what we've heard yesterday is very clear that throughput is also very important. And the throughput is the multiplication, the product of 2 terms. There's eta occulter, which comes from the Coronagraph itself, and eta PSF, which comes from how much of the energy of the PSF is concentrated in some region of the focal plane. And so, some of the PSF, is already affected by this entrance aperture, so it's pretty bad. But then when you null starlight, for instance, with an HLC or with an SPC, you actually manipulate the light even more. And the result of this is this particular PSF, which you can see is very extended, much more than you would expect from a 2.4-meter telescope. So a lot of the energy is still concentrated within 3 lambda over d, maybe 50% of the max. But a lot of the encircled energy is also at greater distances. So for planets, when we're still going to suffer from that and from disks. In fact, you will see that it's favorable in one way and disfavorable in another. But I wanted to because you don't know where the light is coming from, but it's a very extended PSF, and so I wanted to highlight that because that's going to be one of the major differences between JWST and Raman, or Raman and HWO, which is, for HWO, we need that core throughput to be much higher. The core throughput for the Raman coronagraph is around 4%. For HLC or SPC, we need to have it around 50% for HWO. So what does that mean for disk versus planets? Maybe it's been said yesterday already that even though you're looking for planets, you do detect a lot of disks. Serendipitous disk for some, but I think it's going to be even more true with CGI, and I want to illustrate that by this graph here. So what I computed here is just the how much flux you're getting from the system for different distribution on the sky. So this distribution on the sky is represented by that dotted curve here. So for instance, if you look at an exozodi, you're going to look at something which is very extended and centrally peaked. And what the instrument will see, imagine it's lossless except for the coronagraph. You would get the solid black line here. So it's very different from what nature has provided to us, right? And what I showed in the dashed line here is what you would get from a point source at these different locations. So what's happening is if you look at the point source, a lot of its light is being spread out, and so you only look at 5% of it. But if you look at an extended source, like a disk, of course, different regions of the disk will still contribute to that source. And that amplification factor, if you will, really depends on the source brightness distribution. So it could range from 2 to 20, 2 when it's as point-like as you can make it, which is a very thin ring, and 20 when it's a very extended Zodi-like structure. So we'll need forward modeling to assess where the flux is actually coming from, but I would say that we would get a lot of light from disks, no matter what, with CGI. So that's both a property and a difficulty. In terms of community participation, we have the Community Participation Program, which has together a number of external researchers which have been selected in the US and that we pay, and international partners in the countries which have contributed hardware. So France, Europe as ESA, Japan, and Germany. So I want to make it clear here that this is not only end users, observers. They've been really fantastic at helping us shape the mission, the observation, the data pipeline, the planning tools, etc. It takes a village. And we've been very, very happy of seeing them really integrate the instrument team and help us. So we've selected the CPP proposals in 2022 and 2024. So we have a number of selected PIs. You can see the names here. Some of them have been in coronagraphy for a long time. Some of them are younger, less senior people who also help us. And also a number of people with them also have contributed a lot over the last few years, and we are very thankful for that. Yep. Yep. Okay, so as a summary, the coronagraph has matured multiple key technologies to lay the foundation for HWO. Already in the lab, but even more in space, where we're going to try out this in the relevant environment. The coronagraph was delivered to Gordon in May 2024. is TVAC results on the instrument itself have demonstrated performance at least 4 times beyond requirement. The outlook of improving for some use of best effort modes on the sky is pretty good from TVAC testing and some different budget of the guys we got in 24 and 25 from NASA. The CPP started in 24, I believe, supporting observation preparation and broader community engagement. In particular, last year, we wrote a call, the CPP, Beth Miller, etc., wrote a call for community white papers, which was the opportunity to influence this process and the selection of targets. There might be another process like this later on if we have demonstrated good enough performance. But this one was a really big success with over 70 white papers submitted. I think this will be an instrument which is more sensitive to faint extended disks that mature exoplanets, simply because of the physics behind it. But the full observational potential of this instrument will go beyond what we can imagine today and will be for you to realize. And I thank you, and I'll take questions.
Thanks, Bertrand. So we have time for questions in the room. So.
Hey, Bertrand, thanks.
Start here.
Oh, great. Can you? So Bertrand, great. Thank you very much. After looking at your PSF, John Christ and I will no longer have to apologize for the NIRCam PSF.
Happy to provide.
But more importantly, you've done what we did, which is focus a lot on the optics and the PSF. One of the things we found with JW is the detectors and their pixel-by-pixel properties were, in fact, very important as well. To what extent have you started to characterize the detectors for their properties and how that might fold into the final performance?
Yeah, so it would be really for Nathan Bush to answer you, but because they are specialists for detectors. But there's one mode which is extremely sensitive to detector non-uniformities, which is polarimetry. Because in fact, for polarimetry, you're making images at different parts of the detectors and subtracting them, for instance. So we have some means to actually measure the darks of the detectors with high precision, and it's on extended targets. So I know that there's been work done for the polarimetry mode, but that's applicable for other modes as well that takes this into account. Yeah. More details with Nathan.
Hey, Bertrand.
Yeah.
Can you talk about what's sort of the best case for how long it will take to dig a dark hole on orbit?
Yeah, so that's a loaded question, but it's a good one. So the first time you dig a dark hole, it may take many iterations. And what we think is that if you stay in the same hole, let's say HLC band 1, the second time you do it, it will take much less time because you will start from something which is close to the solution. So Eric, I guess we'll talk about this next, but I think that we're talking about 100 hours, 50 hours. It's very long to dig the dark hole, so there's going to be a lot of downtime because of that. Yeah, and
Dimitri.
Great talk. Can you tell us what opportunities there is left for the community, us in the room here, who are not already part of this or the CPP, to contribute to CGI?
Yeah, so there will be probably some more calls also to influence what we observe with CGI, but I would say right now what exists is really a mean to influence CGI via the CPP. So if you're not on the CPP, I would really strongly encourage you to find your favorite person on the CPP and try to influence that person. But yeah, it's a fairly big team, so I mean, I'm pretty confident that you'll know some of them.
Bertrand, so you listed 4 types of observations, so self-luminous planets, reflected light planets, the 2 types of disk observations. Is that an exhaustive list of the kinds of targets you will look at during the technology demonstration? Because
I think
at some point, there was the idea that we should just demonstrate TTR5 on a companionless star. So what's the balance of the priorities here?
Yes, so you will see that we try to come up with an observing plan that includes the usual suspects of disks and planets, but there were also some white papers about brown dwarfs and a lot of calibration originally that we will have to do also, either as part of the commissioning or as part of the first 6 months of the mission. So we did take that into account. There were also, as you're talking about, maybe slightly exotic possibilities. There are 2 that come to mind. There's one about H-alpha, which is the observations of planet information. So we thought that originally, for the first 6 months of the mission, at least, they didn't make the cut because they are too difficult. And at 660 nanometers, you need to be observing in band 2, which is not our first band for spectroscopy. But and another one is planets around binary stars, that Russ knows well, which which is also of very, very high interest to us, but may not be done initially, and I didn't talk about them. I think they will later. There's a poster by Eduardo on that.
It's not a question. Can we ask you to stand on the other side of the podium so folks online can see you? Sorry about that.
Hey, Laurent Poirier from Space Telescope. It's an answer to Dimitri's question, but correct me if I'm wrong. In terms of community involvement, the data will be public.
Yeah.
There is no proprietary bird or anything.
Yeah, that's right.
And a lot of the things we saw on web over the past 2 days were done by people who were not involved with the GTOs, not involved with the GOs. They just got the data on the archive and went to town with it. So I think there's a big opportunity there.
Yeah, thank you, Laurent. I think that I was thinking of what you can do to influence the observations before they are taken, but clearly after they are taken, it's fair game for everyone.
An additional comment, not only the data, but the tools. A lot of the tools are actually already public, and you can already start playing with simulations and, exert yourself with all the, get acquainted with all this data, basically, that is coming.
Yeah. And you can find these tools here, or links here.
Any other questions? Over here.
Yeah. Great talk. How flexible will it be if you have target of opportunities?
Oh. I don't really know the answer to that. Maybe Vanessa does. Yeah, Vanessa does, I think. That's a good question, Mari.
Yeah, I mean, I would say Roman and CGI in particular are not really set up to be target of opportunity in the sense that you hear about them, say, for, fast turnaround, a couple days kind of target of opportunity. But we, here are planning on a few month time scales, and we're not going to plan the entire 18-month mission, set it in stone, and then launch. So there's an opportunity for adjustments along the way, and maybe Eric would like to add to that in his talk right now.
So let's say if there's another great object that you discover in the next year and you want to submit it to us, just write to Vanessa and I will find a way. And Skylar.
Yeah, I'll just add the target of opportunity idea is, it's not only relevant to CGI, it's also relevant to WFI, who's doing the big survey observation. And so at a Roman level, we've been thinking about targets of opportunities. I think at the maybe 2-week time scale is about what we're thinking right now, is what we're capable of doing running through the whole ground system process. It may even get faster as we get some knowledge of how Roman operates, but that's what we're thinking at the moment.
Yes, sorry, do we have still, I think we still have a few minutes, right?
That's good.
So can you say a few words about contingency plans or failure modes for CGI? Is the CPP planning for these scenarios, or is everybody hoping for the best?
Well, definitely success-oriented, I think, in our philosophy, but we're not completely naive. You know, all of us have been humbled by hardware one way or the other over the years, and so you will see that, I think, in Skylar's talks, but we start quite modest and increase over time. So, you know, we don't know where we're going to end up. We certainly have the desire to push the instrument to its limit, to understand what the limits are and what the difficult points are, the challenges are for future missions in particular. But I don't think that there is really a group that says, okay, you three, you look at the case where it's going to be 10 minus 6. You know, I don't think that's happened yet. I volunteer.
I have a question sort of building off that. I'm curious what the general vibe is around trying stuff that's safe versus risky. Like if you're trying to demonstrate something for HWO, I can see a vibe where you want it to definitely work and show the public that it works, while also trying to, what about like trying innovative wafer and control strategies? And so I'm like curious what the vibe is around sort of higher risk.
Yeah, I think like you're asking where the cursor is between being safe and risky.
Yeah, I'm curious what the vibe is with the leadership.
Yeah, so I think that for the I mean, it's kind of an interesting question because there's been a kind of a difference between what people say and honestly the money or the time that we get, right? And so I think that we're going to get less risk adverse as time goes by. If once we have demonstrated TTR5, people are going to relax a lot and try some more exotic modes or wavefront control techniques. You know, the risk of breaking the instrument is less as time goes, and you've already demonstrated the minimum basics. Yeah.
Yeah, my name is Charlie Necker. I worked on Roman, and I'm working on HWO right now. From my perspective, the great value of Roman CGI is demonstrating how well we have done at predicting the performance of the coronagraph and of the observatory. We're doing all the same things on HWO that we did on Roman to try and predict how well this is going to work scientifically and also just technically at the instrument level. And to the extent that we can do lots of experiments that have scientific value, the great value to me on HWO is seeing how well our predictions are working out, because that will tell us how well we can predict what HWO will do.
Yeah, thank you, Charlie. I mean, two things about this. I mean, the tools are the same, roughly, for CGI and HWO. So there's a lot of model validation that will occur with CGI to make sure that our models are currently predicting the performance in polarimetry, for instance. You can only test that in space because you need the primary and secondary mirrors to be there that generate most of the polarization effects. Are there commensurate with what we predicted at that level of CGI? We don't know yet, but that will be one thing we will check.
Jules Fowler from UC Santa Cruz. So you mentioned that you were thinking about doing observations of companions and then polarimetric observations of disks.
Right.
If both of those are successful in the initial phases, is there any room to do polarimetric observations of companions, especially considering you could get the full intensity images from those data?
Yes, I think so. I mean, it's not ruled out. I mean, you know, seeing the polarized signal is going to be difficult, but it's certainly something that's been suggested and we would think of doing in the extended phase. Yeah.
Any more questions? If not, let's thank Bertrand again